Hello and welcome back to the course Physics 141 Classical Electromagnetism 1. So before we start, let's first review some of the lessons that we have or that are needed for today's session. So in your Physics 21 Mechanics course, you have discussed about how to calculate the work done by a force. So in general, the work done by a force is just F dot force times distance, F dot dl. So this is the work done by a force in moving, say, a particle from A to B. So in the previous lesson, we also have discussed about the potential difference between 2 points, A and B. So it's just E dot dl, the electric field dot with the differential length. So for today's lesson, we will be talking about work and energy in electrostatics, or electric work and energy. So how do you calculate the energy of a system, whether a system is a discrete charge distribution or whether the system is a continuous charge distribution, and relate it to work. How much work is needed to assemble this system? So we will have some examples, and basically we will just review some of the concepts that you have learned in Physics 41 on work and energy. So if you want to move a charge, and say there is an existing charge distribution, and you want to move a charge Q from, say, point A to point B, say along this path dl, notice that this charge Q will experience an electric field equal to Q times, electric force equal to Q times E, where E is the electric field at the location of Q. So from our basic definition of work, if you want not the electric field but U, if an external force wants to move a charge Q from point A to point B, then that the force exerted by that external force is just basically the negative of this, the negative of the electric force. Take note that if for this specific charge Q here, the electric field is, the electric force is in this direction. There's an electric force in this direction. So if you want this charge to start at point A to be static at point A, so you need to apply a force with equal magnitude but opposite in direction, so that this charge will stay at point A. So at all points from A to B, you must be applying that opposite force so that you can move the charge from point A to point B. So therefore, this force here is the external force. It's the force applied by you, and it's just equivalent to negative QE, the equal in magnitude but opposite in direction to the electric force here. And since, based on our definition, negative E dot dl, it's just the potential difference between point A and point B. Now if we take our point A as our reference and it's at infinity, and our point B at our field point, say R, then this becomes the work done by an external force in moving the charge from A to B, or from infinity to R rather, is just Q times the potential at R, since we are assuming here that the potential at infinity at point A is 0, since it's very far. And take note, potential is inversely proportional to R. So when r approaches infinity, 1 over infinity is a very small number, or approximately 0. So this is the work done, or the energy expended, or energy needed if you want to move or place a charge q starting from infinity to the point r, where the potential at point r is v. You can also think of this, since from your Physics 21, you have learned that basically when you're doing work, you are just actually giving energy. If you're doing work on a body or on an object, you're actually just giving energy to that object. So the work or the energy that you expend in doing this, in moving the charge from infinity to point r, that energy expended will become the energy of the charge, or the something what we call we can also call it as the potential energy of the charge. So since similar with gravitational force, electric force is a conservative force. So the path doesn't matter. The path, the dl, no matter how wavy is the path or direct is the path, it doesn't matter. Only the initial and final points matter for conservative forces. So let's first try to solve what is the energy of a discrete charge distribution, and it's basically the work done in bringing all the discrete charges from infinity to your final position or final location where your charge distribution is located. So suppose you have a discrete charge distribution q1, q2, q3, qj, and you are asked to find. So in order to find the energy of this distribution, is basically just the work done in bringing all of the charges from infinity to their respective positions. So you will bring q1 from infinity to its position, say here, and since for the first charge, since there are no other charges present left, then the work done in bringing that charge from infinity to this point will be 0. So this, because there's no other charge, there's no potential, there's no v, there's no potential due to the other charges, there's no, you can think of this, there's no resistance. So the work done will be 0 for the first charge. So for the second charge, say q2, you bring it from infinity to this point here. Since there's already a charge here, q1, and this q1 will have a potential at this location at r2, then therefore from our previous equation for work done in moving a charge q, so it's just q2 times the potential at r2, the location of q2, due to q1, v1. So in this case, the potential of v1 at the location of q2 is just q1 over r12. r12 is the distance from q1 to q2, the separation distance. Or simplifying, we get this equation. Now if we want to get the third charge, the fourth charge, or the jth charge, then it's just the same. It's just the jth charge qj times the potential at the location of the jth charge due to the other charges. So you will have a summation term here. So qi, qj, rij, where i is less than j. Now if you want to find the total work done in assembling that discrete charge distribution, this system, then you have to add all of the work done in bringing each of the individual charges. And this will require you to, instead of having this summation, we can just have this double summation here. Actually, this is a double summation. There's a summation here, and if you sum over this summation, then there's a double summation. But instead of having I is less than j, we can actually just say I is not equal to j. But since if you have q1, say for instance I is equal to 1, j is equal to 2, you will have q1, q2, but you will also count your count will also include q2, q1, which is just equal to q1, q2. So this double summation will actually give you a double count, a double counting. That's why there's a factor of 1/2 here to negate the effect of double counting. So you multiply by 1/2. And rearranging the term, this term here will just be the potential at the ith charge location, Ri, due to the other charges. So that one, so generic. This is the generic na total work done, or the energy expended, energy used, if you want to assemble a discrete charge distribution of n charges starting from infinity. And of course, this will correspond to the energy of a discrete charge distribution, which is in this case a system of n point charges. Note that you can use this equation if your number of charges is very large, but if you just have 1, 2, 3, or 4 charges, you can just solve the work one by one and add them together and not use this equation. So let's have an example. So suppose you want to make a square charge distribution. So this is your square, side A, and you have 4 sides, you have 4 corners, and you place 4 charges at every corner. Charge 1, Q1, Q2, Q3, and assuming you already have set up Q1, Q2, and Q3, and you want to bring a 4th charge, a positive charge Q, from infinity to say 0.4. So how much work will be done in bringing this 4th charge from infinity to 0.4, and what's the total work done in assembling the whole system? Okay, so for the first problem, the work done in bringing the 4th charge is just Q4 times the potential at R4 due to the other charges, Q1, Q2, and Q3. So this V123 is just the addition of the potential due to Q1, Q2, and Q3. So the potential due to Q1 at 0.4 is just K, which is 1/4 pi epsilon naught, Q1, which is negative Q, over R14. R14 is distance from Q1 or 0.1 to 0.4, and that is just, in this case, this side A. Now, for the potential due to Q2 at 0.4, so this is Q2, we need to find its potential contribution at 0.4. Then you have K and then Q, which is positive, so this one, over R24, which is the distance from 0.2 to 0.4. So since this is a triangle, a right triangle with 2 sides A, then this is square root of 2 times A, the diagonal. And similarly for the contribution of the 3rd charge, Q3, its potential at 0.4 is just K, then its charge is negative Q, over R34, which is just the distance A. So using those values and simplifying here, so our Q4 here is positive Q. So these are all Q's here, so you will get a Q squared. So you can add actually these 2 terms here. You will have negative 2, you have 1/square root of 2, and this will be your final answer for the first question. This is the energy needed if you want to bring a 4th charge positive Q from infinity to 0.4 here. Now, To find the total work done in assembling the system, we can use the general equation, or we can solve each of the work done in bringing each of the charges from infinity to their respective positions. So for bringing the first charge, of course, there's no resistance, so zero work done. For the second charge, it's just Q2 times V1, where V1 will just be the potential of Q1 at the location of Q2, and this will give you this value. For bringing Q3 from infinity to this position, it will just be Q3, which is negative Q, times the potential due to Q1 and Q2 at 0.3. So V12 at 0.3 or at R3 is just given by this value. And of course, we have solved the work done in bringing the fourth charge to this position. So taking all of those into account, so we get the total work done is just Q squared over 2 pi epsilon naught A. So it's actually just twice the work done in bringing the fourth charge from infinity to 0.4. And this is now the energy of your system. So this is the energy expended by an external force in assembling the system. So therefore, this will also be the energy which will be used by this four system of charges in disassembling. If they want to disassemble the distribution, this is also the energy needed in disassembling the system. Okay, so basically they use the energy given to them to disassemble themselves. So it's potential energy, just like in a spring. So if you stretch a spring, you're actually doing work on the spring, you're actually giving energy to the spring, and that energy will be used by the spring in order to return to its equilibrium position. Okay, so let's now go to continuous charge distributions. So suppose you have a continuous charge distribution, volume charge distribution, for example, in a volume d tau, and we can just actually use an analogy. So we have derived this in the previous slides. So the total work done in bringing a system of discrete charges Q sub i's is given by 1/2 summation of QV or VQ. We can do the same if we convert this into an integral na form. It's just 1/2 V, and the summation of Q will just be the integral of dq in integration. Okay, so since dq can be replaced by rho d tau or sigma dA, so in this case, since our charge distribution is a volume charge distribution rho, then we can replace dq by rho d tau. Take note, our volume here is tau, it's not v. V is our potential. So this is now the energy of a continuous charge distribution. However, we can also use Gauss law and this vector calculus formula, that the divergence of the product of a scalar function f and a vector function a is just given by this. So using the value of the electric field as negative, the negative gradient of potential, we can also write this equation in terms of the electric field. So it's just the same. These two are just the same, the energy of a continuous charge distribution. So if you are given with a charge density rho and potential, then you can use this equation to solve for the energy of the energy of the continuous charge distribution. But if you're given with the electric field, then you can use this equation. So any of the two will do depending on the given values. So for instance, let's try to find the energy of this charge distribution. So it's a uniformly charged spherical shell of total charge Q. So it's a shell, meaning all of the charges Q, the total charge Q, is uniformly distributed all over the surface. There's no charge distribution inside. See, this is a shell, it's hollow. Okay, so for solution 1, we use the first equation. So the V dq, where our dq here, since this is a surface charge distribution, we will replace dq by sigma dA instead of rho d tau. So using this, since we already know that we have already solved this problem in the previous lesson, and the potential inside the sphere is k q over capital R. It's constant because there's no gradient in the electric field inside is 0, meaning there's no gradient in potential, meaning the potential is constant. So we can use this value. So since this is constant, the V is constant, potential is constant, we take it out of the integral, and we are left with integral of sigma dA. And integral of sigma dA is just the total charge, right? dq. Integral of dq, so q. So the answer of this integral is just q. So you replace that with q, and then V is just given as this. So the total energy, or the energy of this continuous charge distribution of this uniformly charged spherical shell, is given as q squared over 8 pi epsilon naught r. So since for this problem we also know the electric field inside and the electric field outside. Electric field inside is 0, electric field outside is just kq over r squared. So we can also use the second formula. So take note that in this formula the integral is over all space. So meaning from 0 to infinity. Now, you can actually divide this into two integrals. So you will have integral from, say, inside, from 0 to capital R of E squared d tau, and this electric field is the electric field inside, plus the electric field integral from R to infinity of the electric field outside squared d tau. So this integral is actually two integrals. There are two intervals, from 0 to R and from R to infinity, but it just so happened that the electric field inside is 0, so this first integral here is essentially 0, and this integral will just be equal to the integral from R to infinity. Okay, so take note, this is a volume integral, so only the R component is from R to infinity, but the phi and the theta is from 0 to pi, and the phi is from 0 to 2 pi. So the differential volume here is the differential volume in spherical coordinates, r squared sine theta dr d theta d phi. So you have triple integral. It's a triple integral. So for the r component, so you square this. So the square of this is q squared, and then you have 4 squared pi squared epsilon naught squared r to the 4th. And since there's an r squared here and there's an r to the 4th because of the square of this value, then you will have 1 over r squared, dr over r squared. And then you will have sine theta d theta d phi. So of course this is just 2 pi, and the integral of sine theta from 0 to pi will just give you 2. So basically these two terms here will give you 4 pi. So 4 pi, and this is just basically 1 over r, or sorry, negative 1 over r, but your limits here are from infinity to r. So you will have 1 over infinity minus 1 over capital R, and the negative sign, there's a negative sign, there's a negative sign, and your final result will be positive. So try to verify this result here. It's just an easy integral. Okay, so that's the end of the lesson. So we are now actually nearing the end of the first chapter on electrostatics. We only have 2 lessons left conductors and capacitors. So for our next lesson, we will be discussing about conductors, some basic properties of conductors, and how to deal with how to find the potential, the electric field of a conductor. So that's the end of this lesson, and I will see you in the next session. Thank you.